Okay.
So thank you very much for the invitation, and sorry for the mix-up, and thanks, Hans. Let me know if you have any problems with seeing things now. So everything I talk about is going to be joint work with Charles Delman. And we're going to be now moving to the context of thinking about M as just a connected, compact, orientable three-manifold. And we're going to be thinking about codimension one foliations of our manifold. And that just means we have a decomposition of our manifold into surfaces so that locally the surfaces fit together nicely. Locally, if we think about covering our manifold with a foliation chart, locally we look like R3 and the leaves meet the R3 just in horizontal planes. And we're going to typically be thinking about co-oriented foliation. So we're going to be thinking about every leaf comes with a co-orientation, and these co-orientations are compatible. So when we think about this local chart structure, we can think about the co-orientation may be given by pointing in the vertical Z direction. And since our manifold is oriented, sometimes I'm going to think in terms of the leaves being oriented compatibly, and sometimes I'm going to be thinking in terms of this transverse orientation. And you can think, okay, so you've got this manifold, you're thinking about your favorite manifold, it's decomposed as a union of leaves. And maybe you've made some choice where the tangent plane field isn't even defined. But there's a result of Caligari which says, well, you can always isotope your foliation so that the tangent planes to each of all the surfaces, the tangent plane field, that two-plane field is well-defined and continuous, and the leaves themselves are smoothly immersed instead of embedded, because typically I'm thinking about these surfaces as being non-compact. And non-compact in a compact manifold, I can't hope for embedded. So some elementary examples, we could think about a manifold being fibered. Maybe a manifold, we have some compact surface S, we have some homeomorphism S to itself. We're thinking orientable manifold, so we're thinking orientation preserving homeomorphism. And a manifold then is just take the I bundle S cross 0, 1 and glue the top to the bottom using that homeomorphism phi. So identifying X1 with phi of X0. And then the foliation is just the union of that disjoint, that decomposition and the union of fibers. There's a foliation of the solid torus that plays an important role. And the foliation is called a rape component. And here are my attempts to draw the picture, but it's a foliation of a solid torus where you have a single compact leaf, the torus, and then you have a disjoint union of copies of R2, where the R2s, as you move out to infinity in an R2 leaf, you're spiraling around that torus leaf. So each R2 leaf, if you take its closure, you're going to see that compact leaf T2. And another way you could think about getting the rape component is to say, okay, well, start with a solid torus. A solid torus is certainly fibered by meridian discs. We can think about the leaves being D2 cross theta, where theta is in S1, and then modify that foliation by meridians by just saying, okay, as you get closer and closer to the boundary, instead have that boundary spiral around the torus. Or you can think, okay, I can form surface of revolution, and I can then glue top to bottom, and I see my leaves by piecing together. I've just shown a few pieces. And then more generally, we can play this spiraling game. I could think about, let's just think about start with your favorite fibered link in S3, say. You can take the foliation by the fibers. The fibers are going to meet the boundary of the neighborhood of the link transversely. But again, you can just instead modify your foliation so that the boundary of the neighborhood of the link lies as a leaf. And those fibers become non-compact leaves that spiral around each of the boundary components. And here's a schematic picture of this. Or of course, I could take two such pictures where I've spiraled things so that I have the boundary of the neighborhood of the link included in my picture, just glue along those tori, and you have a foliation of the thing you got by gluing together those two link complements. Okay, for the most part, I think of those examples as being bad examples or boring examples. I mostly care about foliations that are taut. And so a foliation is taut if, well, depending on the literature, what you're reading, co-oriented is included or not. But for today, when I say taut, I'm going to be assuming co-oriented. And if there are no dead end components, so you're not going to be in any of the examples that I showed before, where I have torus leaves that co-bound an oriented submanifold of the manifold. So taut means I don't see some disjoint union of tori. Remember, my foliation is co-oriented, and so the condition is I don't see a union of leaves which are tori, which separate my manifold, so that the co-orientation on the boundary tori all point into the submanifold or all point out. And equivalently, that means that there's a topological transversal to my foliation that has non-empty intersection with every leaf. Or equivalently, there's a topological transversal to F that has, for every compact leaf, there's a topological transversal that has non-empty intersection with each compact leaf. So lots of different ways of thinking about taut. Taut means that there aren't these tori that are somehow separating your manifold into pieces. And a natural question is to say, well, which three manifolds contain taut foliations? And classical results tell us, well, if we have a taut foliation, we're irreducible. Any S2 in R3 manifold bounds at 3-ball, and the universal cover is R3. And more recently, Ashvath and Szabo tell us that, well, in this case, we're not in L space. But we could instead say, okay, let's be greedier and say, well, suppose I give you a manifold, you know, how many distinct foliations are there in my manifold? And if you are used to thinking about foliations, you quickly think, well, I need to have some useful equivalence. And there isn't really a agreement or a best notion of equivalence. In part that depends on what you're interested in. Maybe you really are interested up to isotopy, in which case if we have a taut foliation, we're going to have lots and lots of foliations. Or maybe you're thinking about homotopy classes of two-plane fields, or maybe you're thinking about some sort of, you're allowed your two-plane fields of your foliation to be perturbed, but not too much. Maybe they can, the Gabbai has a notion of coarse isotopic, or Ellie Ashberg-Thurston, maybe you could approximate your foliation with contact structures and use classification of contact structures to talk about things. Or maybe you could think about corresponding keyguard for all classes. There are lots of different choices depending on what you are interested in doing. Okay, so let's think about this question about existence of foliations. And we know from Gabbai that as long as my manifold is irreducible and not a rational homology sphere, then there's a taut foliation. And if you want to be greedy, you could say, oh, okay, well, what if I'm interested in all possible taut foliations? Maybe that's too difficult. Maybe first I want to think about restricting to finite depth foliations and start thinking about using maybe homology or cohomology classes to describe what I see. And then you can turn to, well, what happens if I'm not in this world? What if I am a rational homology sphere? Or what, are there other foliations more generally? And Charles Delman and I over the years have developed a collection of constructions, and, slightly different, slightly, there's similarities. They're very much in need of a unifying theory, and we don't have that yet. But today I want to talk about one of the constructions, which is the notion of what we call double diamond taut. So here's the setup. So I'm quickly now jumping from trying to define everything to talking about sutured manifold theory. But let me try not to think too much about sutured manifolds. And let's suppose we just start with a manifold and we have some knot in the manifold and we're in a nice enough world that our knot has a minimal genus Seifert surface. Let's call that R. So we've got this manifold, we've removed a neighborhood of the knot, and now we're thinking about removing a little open thickened neighborhood of the Seifert surface also. So that's what this notion M minus neighborhood of R, A of boundary R means. It just, we're taking away minimal genus Seifert surface and we're keeping track of the annulus on the original boundary. So if we think about boundary R, it cuts out boundary torus along a simple closed curve and the complement is an annulus. So that's just what this A of del R is. And then I'm saying, oh, okay, let's look in M minus neighborhood of R. And let's think about what surfaces we see in the complement of this R. And that surface is going to travel along R. Well, I lied a little. I was telling you I was removing a thickened up R. And in this picture, I've just removed R itself. And that's closer to the way I want to think. So maybe let's think in terms of this picture right here. And the game is going to be, well, del S does what? It travels around the boundary of neighborhood of R. And I'm going to say, suppose locally I see a picture like this. So locally I see that the boundary of S crosses the boundary of the neighborhood of the knot. It crosses R. It crosses the boundary of the neighborhood of the knot. It crosses R, and then it goes on and it does whatever it does. But what is important in this picture is that this region right here is separated off. And let's see, do I really want to say equivalently here? I don't really want to say equivalently. I want to say, for example, maybe we see something like this. So maybe when we're thinking about our minimal genus Seifert surface, we see three consecutive half twists. And maybe they're left-handed or maybe they're right-handed. The picture I've just removed from view is, I think, corresponding to this first one on the left. And so the game is to say, okay, if I am thinking about this picture, we started by thinking about removing a neighborhood of a knot. So we're looking at the knot complement. And then we're thinking about taking the union of the minimal genus Seifert surface R together with this second surface S. And if you're familiar with Gabai's theory of sutured manifolds, you know that associated to this cutting first along R and then along S is a branch surface. And when I draw these pictures, the arrow is meant to say, okay, my bottom hand, say, is the surface R, and S is a red surface that's coming in transversely. R and S are both co-oriented, and we pinch to a branch surface, so we smooth along the intersection so that the tangent plane field to the union is defined, and in such a way that the co-orientations match up. So the arrow just means if I see this picture right here, I pinch, I sort of smooth things out. The surface S approaches the surface R tangentially, and the pinching is in the direction of the arrow points into the cusp or the suture that we've created in this way. So the game that Charles and I play is to say, oh, okay, as long as we see this picture in the first two steps of a Gabai sutured manifold, well, forget sutured manifold. If you see, if you can cut open along S so that the resulting sutured manifold is taut, then we can play games so that instead of just realizing some small interval of slopes, one can realize all possible slopes. One can construct foliations that realize all possible slopes except for the meridian, the sort of that's naturally pictured in this picture right here. Okay, so the game that I want to describe in a few minutes is, if you see this, then there's families of taut foliations that realize that meet, you give me any slope besides the meridional slope. There's a taut foliation that meets the boundary in parallel curves of whatever that slope was you gave me. So if you give me slope 2/3 or slope 105/7 or slope pi or whatever, as long as it's not 1/0, there's going to be a taut foliation that realizes those slopes. And I talked about a branch surface, and I'm going to call the branch surface that comes from just the traditional Gabai game is just b to the g, g for Gabai. And it's this thing we get from taking first the surface R and then the surface S and pinching to a branch, smoothing to a branch surface. And an example where this is going to always apply, for example, is if you have a plumbed band that's not a Hopf band. So if you can Murasugi Disan, a Hopf band, but sorry, a plumbed band. But more generally, if you see some picture like this. Okay, so the game we play is pretty simple. So you take the branch surface, and we're going to add a torus that's boundary parallel in the interior of the complement of our knot. We're going to add a copy of the boundary. So we're just going to add a boundary parallel torus. And then we're going to truncate R and S so that their boundary lies along this copy of torus. So we're going to remove sort of the annuli in a neighborhood of the boundary. So we now have surfaces R and S. And we're going to form a new branch surface B prime that fully carries the lamination L, and for which we know things are really, really nice, because the complement of this new branch surface is going to be almost exactly the complement of the branch surface we began with. And we knew that one had taut complement, unioned with one other region. This is going to be the region around the knot. And the region around the knot is just going to be, well, we're going to have modified in our branch surface our picture so that the original boundary parallel torus we added now has two meridional cusps. So we've got this picture you should be thinking about. There's a circle's worth of cusps, a circle worth of cusps going off to infinity. And whenever we see this picture, we're really, really happy, because this complementary region can be filled in with leaves that strongly realize any slope except the meridional slope. So we can fill in with leaves so that whatever slope you give me, as long as it's not this one right here, is going to, I can find a taut foliation, we can find a taut foliation that meets that boundary torus in simple closed curves of that slope. So again, the underlying set is just T and R and S, which were truncated. And away from that 3 half-twist region, the branch surface is going to look exactly like the Gabai branch surface, except this added torus is going to replace the role of the boundary of N of kappa. And in the 3 half-twist region, we're going to have the following picture. And the following picture, I'll try and go through a little bit slowly. Okay, so here in the middle is that picture we had before. We've got this rectangle is just a piece of rectangle of our surface R. And this doesn't need to be a disk, but it does need to be a distinct component that these two edges disconnect my surface into this piece and then whatever's happening outside. And the red surface, so the surface S, is what's marked in black here. So it's dot, dot, dot behind dashed here is on the other side of my R, crosses the boundary of the neighborhood K, crosses over here, crosses behind, and then comes along here. And what we do is we change the behavior of the branch surface in the neighborhood of these pieces in the way that's shown in these pictures. So I've added color here. So blue now is the R, the minimal genus Seifert surface that we started with. And if you look at what we're doing, our R is just a piece of surface, comes down, wraps around behind, comes down. Started at slope 0. Except now something very different is happening with our branch surface, because our branch surface does not carry R. If you notice the blue now has an arc of cusp. Instead of the R being a smooth surface, it has a suture along the surface. And so we have this R, and then the S cuts over here. So the diamond is saying, along this diamond, our surface R is not smooth. Along this arc, it has this cusp region. So we travel along here, and then we wrap around. And over here, where we have this other letter C, again, if you think about what's happening with the blue surface, we've joined it at this cusp. We wrap around with our R, and we have another cusp corresponding to the diamond that's not shaded in, that's on the other side. We travel along and around, and we get over to this picture right here. So we're thinking about traveling underneath. We have, again, our blue. This time, the blue is, the blue is supposed to be smoothly embedded on one of the sides. Yes, so as we move around, we have the blue as it's pictured right here. So around here, we see this picture. Around in this neighborhood, we see this picture. And in this neighborhood right here, we see this picture. So all that's happened is we've taken this branch, this set, which was R union S union T, and we've chosen to smooth it to a branch surface in a way that creates sutures along the surface R, so that we get a branch surface that no longer covers R. No longer carries R. And where we have a C, if you look at what's happened, there's this circle interior. If you go back to this picture right here, we have these circles worth of sutures on the interior of this complementary region that contains our knot K. At each knot crossing that's labeled C, there's one of these cusps. So over in this neighborhood here, and in this neighborhood here. But over here, we just have a tube that's going all the way through. So we sort of have, maybe it's easier to look in this left-hand picture, we've got a tube, and maybe there's a skirt, and then you've got the regions joining top and bottom, but the tube is just running smoothly through. And if one looks at the picture and is used to thinking about sutured manifolds, and you want to keep track of the sutures, those are what are marked in the red. So we have this dashed suture that's going on and joining whatever was going along the A of boundary R before. We have sutures coming along A of boundary R behind, coming across here, wrapping around and doing this and doing that. And if you're used to thinking about sutured manifolds, that means that the sutures behave exactly as if we'd smoothed the branch surface in the usual traditional way of just using the co-orientations on R and S to smooth to a branch surface. And that means exactly that the complementary region of the new branch surface is just, we have the complementary region that doesn't contain K, and that complementary region looks exactly like the original complementary region from, I guess there should be a G superscript here. But we've added sutures to the surface T that started off as a smooth torus, so that we now have every dane filling except the one corresponding to this slope 1/0 is going to allow you, you're going to have a foliation that meets in that slope and can be capped off to give a taut foliation. Again, I think it's fairly key that the R is no longer carried by the brown surface. It's no longer going to be, you know, essentially tangent to the brown surface. It's no longer going to be fully marked by the foliation. And so question, you know, one question you might ask is, well, what can you say about the Euler class, or what can you say about the contact class of that foliation? And I think I'll stop there. Thanks.
Okay, thanks very much. So is there any questions?
I do have one question, just because you were talking about how, I mean, this is an amazing construction, really, and like the examples. And you were saying that you and Charles are sort of in search of a theory. One of the big questions that I think that I've heard of, right, when I hear foliations, of course, L space conjecture. In these examples, I mean, you're constructing the foliations, and I think you kind of said that the manifold would have to be irreducible, something like that. But in terms of like the other, like conjectured equivalent, the things that are conjectured to be equivalent in the L space conjecture, are you sort of seeing that concretely?
So the only thing that I can say about that is initially we were super excited because this is the first construction where we can see a difference between fibered and not fibered. But now it's been a while and we haven't, you know, been able to make this, you know, some version of this work for non-fibered. But yeah, sorry, let me just stop there. But, you know, it is a construction that works very, very differently in the fibered case and the not fibered case.
Okay.
Thank you.
Thank you for your talk, Rachel.